All right, so now that we have talked about conservation of momentum and we've talked about these mass velocity graphs, we want to set up some problems so that we can use those graphs to solve different problems. All right, so this is actually example 1 on your worksheet. So what it says is ball 1 has a mass of 4 kilograms and it's traveling to the right with a velocity of 3 meters per second. So we've got ball 1 going this way at 3 meters per second. And it has a mass of 4 kilograms. And then ball 2 has a mass of 2 kilograms and it sits at rest. So ball 2 is sitting right here and it has a mass of 2 kilograms. And it's not moving at all. So when we put these onto our chart, remember mass goes along this axis right here, and we have a mass of 4 for ball 1, so we're going to go over 4. 1, 2, 3, 4. And then velocity is on our y-axis, and it's traveling to the right, so we're going to say right is positive. So 3 meters per second to the right, so we're going to go up 3. And this is our mass velocity graph for ball 1. Now ball 2 has a mass of 2 kilograms. So we're going to go over 2. Now it doesn't have any velocity because it's sitting at rest. So what we're going to do is we're going to put little X's in there to show that we've thought about that, right? We didn't just forget to come back and put our velocity, but we know that it has a mass of 2 and we know that it's at rest. So that is our ball 2. Now what else do we know? After they collide, ball 1 continues to the right with a velocity of 1 meter per second. So over here we have ball 1. He's slowed down a little bit and he's going 1 meter per second. His mass is still 4 kilograms. So we don't lose any or gain any mass. And then the collision, what do you think is going to happen here? So ball 1 slows down, but what do you think is going to happen to ball 2? Probably going to start moving, but the problem is we don't know what the final velocity for ball 2 is. We do know, however, that he has a mass of 2 kilograms still. Okay, we didn't break anything. So we're going to come over here to our final conditions, and we're going to go over 4 again because that is the mass of ball 1. And ball 1 is still moving, but it's moving at a velocity of 1 meters per second. And ball 2 is over here, mass of 2, but now we don't really know our velocity. So how are we going to do that? So this is where that conservation of momentum comes in. All right, so remember the final momentum, or the initial momentum, the total initial momentum of ball 1 and ball 2 is going to be equal to the final momentum of ball 1 and ball 2. So we'll have to come over here and we'll have to figure out how much momentum each one has. All right, now ball 2 is pretty easy because it's not moving, so it has a momentum of 0. Now ball 1 has a mass of 4 and a velocity of 3, so it has a positive 12 momentum. And we could put our label on there. So our total momentum in our initial conditions before the collision, we have a positive 12 initial momentum. So what that means then is that the initial momentum is going to be equal to the final momentum. So over here, we have to have a total momentum of 12 for both ball 1 and ball 2 combined. Okay. So when we look at this, ball 1 we know has a mass of 4 kilograms and it's moving with a velocity of 1 meters per second. So ball 1 has a momentum of 4 kilogram meters per second. All right. So now our total over here has to be 12. 4 of that is taken up with ball 1. So what does that leave as the momentum of ball 2? Well, in order to get 12, when we already have 4, we have to have 8 kilogram meter seconds over here for our momentum of ball 2. So how do you get 8 kilogram meters per second out of ball 2? Well, we know that it has a mass of 2 kilograms. So in order to get, you can write this out over here, right? Momentum equals mass times velocity. Oops, let's scooch that over. Momentum equals mass times velocity. So our momentum is going to be 8. Our mass is 2, so what's our v going to be? So we're going to divide by 2. Our velocity is going to be 4 meters per second. So we're going to go up 4 for our velocity. Okay. Now we can double check that, right? How many blocks do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a total of 12 momentums. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a total of 12 momentums. Okay. Now one other thing that we can do, we can translate this into a position time graph. Okay, I know you're thrilled to do that. So let's scooch this down a little bit. All right. So we've got a position time graph down here somewhere. Zoom the other way. There we go. That way we can see it a little bit better. See everything. There we go. All right, so a position time graph, remember, is looking at the position of our ball over time. All right, and we can use our velocity to figure out where our ball is going to be at any given time. So we're going to start by labeling. All right, let's just go 1, 2, 3, 4, 5, 6. Now we don't know how long this ball traveled at this particular velocity. Let's just say it went for 2 seconds. All right, so that way we can kind of fit that on there. So we know that it traveled 3 meters per second for a couple seconds. So what that means is after 1 second, it's going to be 3 meters away. So we can use a scale of 3 over here. It doesn't really matter what you use your scale as. You can kind of adjust it as you start to do that. So if we look at ball 1, he's going 3 meters per second. So after the first second, he'll be 3 meters away. After 2 seconds, he'll be another 3 meters away, so he'll be at 6. After 3 seconds, he'll be at 9, right? So this is the first motion of ball 1. But then what happens to ball 1, right? He has a collision and he slows down. And so instead of going 3 meters every second, now he's going 1 meter every second. And so after this second, so let's just say our collision occurs here. Okay, so this is where we collide. So after the collision, in 1 second, he's only going to be 1 meter away. So he'll be at 10. And then after another second, he'll be at 11. After another second, he'll be at 12. Okay? So what we've done here is we have drawn a position time graph for the motion of ball 1 before the collision and after the collision. Now we can do the same thing with ball 2. Ball 2's initial velocity was 0, but then he got bumped and now he's going 4 meters per second. Okay. Now here's the thing about a position time graph. Ball 1 collides with ball 2. So what happens right here? Right here, ball 1 and ball 2 are in the same place. Okay? They can't collide if they're not in the same place at the same time. So we can kind of work backwards from this. So this is where they collide, but he wasn't moving. So he had to have been here the entire time. He's just sitting here minding his own business. So there's his first motion. But then he collides with ball 1, or actually ball 1 collides with him, and he starts moving with a velocity of 4 meters per second. So he was sitting 9 meters away from our reference point at time 3 when he got collided with. A second later, he's now moving 4 meters per second. So he's 4 meters away. So he's going to come up here to 13. Okay. And then another second, he's going to be another 4 meters away. So he's going to be up here at 17. And then we kind of ran out of space. But then we got another one somewhere about up here maybe. Okay. And he's going to be, let's see, this was 17, so this is going to be 21. All right, so we've got the second motion is going to be 4 meters per second after the first motion was 0 meters per second. So this is going to be a position time graph for both ball 1 and ball 2 before the collision and after the collision. All right, so let's try another one. Let's zoom back in. See it a little bit. All right, so in this one, if you can read that very well, ball 1 has a mass of 3 kilograms. Let me underline that. And is moving to the right. So we've got ball 1 moving this direction. But we don't know how fast. It doesn't tell us right now. Ball 2 has a mass of 6 kilograms and moves to the left with a velocity of 3 meters per second. So ball 2 is over here somewhere, traveling to the left. And he has a mass of 6 kilograms, and it's 3 meters per second. So since he's going in another direction, it's actually negative, right? We want to give it that designation. So what do we know? What are we able to do here? Well, let's see. We've got 3 kilograms for ball 1, but we don't know its velocity yet. So we're going to just kind of draw our mass in so that we can see it. And then we have ball 2 has a mass of 6 kilograms. 1, 2, 3, 4, 5, 6. There we go. And it's traveling to the left, which is negative, for 3 meters per second. Can't draw. There we go. Okay. So that's what we know about our initial conditions. And then they collide. So ball 1's going to change direction. Okay, so ball 1 now moves to the left with a velocity of 1 meters per second. So ball 1 is going to be going this way, 1 meters per second. Now we defined left as negative. We also know it's 3 kilograms. Ball 2 is going to continue moving to the left with a velocity of 1 meters per second. So after they collide, we're still going to be going this way with -1. So it's going the same speed now as ball 1, and it has a mass of 6. So maybe we can figure out the initial velocity, right? That's what we're asking. The initial velocity of ball 1. So ball 1 has a mass of 3 after the collision, and it's moving in a -1 meter per second. So it's going to go this way. Ball 2 has a mass of 6. 1, 2, 3, 4, 5, 6. Doesn't look right. And it's going also this direction. Okay. All right, so let's look at our momentums, because remember, the initial momentum is going to be equal to the final momentum of ball 1 and ball 2 together. So we want to look at this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? So we've got 3 meters per second times 6 kilograms. And so that's going to give us an 18. And it's going to be negative because our velocity is negative. Okay? So right now we have a negative 18 kilogram meters per second as our velocity. All right, so over here for ball 1, we have 3 kilograms times a -1 meters per second. So it's going to be -3 kilogram meters per second. Ball 2 is going to have 6 kilograms and a -1 meters per second. So that's going to be -6 kilogram meters per second. Interesting. So what happens here? Our total momentum at the end, where we know, is -18. No, it's not. It's -9 kilogram meters per second. Okay. Over here, now, we have -18 kilogram meters per second. But we need -9. So how can we get a -9 out of -18? We're going to have to add 9 somehow. So how are we going to get a 9 momentum for ball 1? Okay, so we have a mass of 3. So again, we can actually do this math. Equals mv. We need ball 1 to have a momentum of positive 9 kilogram meters per second. That's going to get us our negative 9, right? Because we need negative 9. And we have negative 18. So in order to get negative 9 from negative 18, we need a positive 9. And we can do this with our 3 kilograms. And then divide by 3, divide by 3. So our velocity of ball 1 has got to be a positive 3 meters per second. Okay, so we're going to go up 1, 2, 3. Go over 1, 2, 3. And this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 3 kilograms times 3 meters per second is going to be a positive 9 kilogram meters per second. So positive 9 and negative 18 is going to give us negative 9. So the initial velocity of ball 1 was a positive 3 meters per second. So what is this going to look like? Oops, wrong way. What is this going to look like on a position time graph? Whoa. Hold still. There we go. So what's this going to look like on a position time graph? All right. So ball 1 is traveling a positive 3 meters per second. So we can put that, we can start our graph. We can do it threes again. 9, 12, 15, 18. I think I did some wrong math over there. So 1, 2, 3, 4, 5, 6. All right. So this is our time, and this is our position. Now again, you can have any numbers that you want. You can have any scale. You just have to make sure you go back and check where you're plotting them. So after 1 second, ball 1 is traveling 3 meters per second. So after 1 second, it's going to be a positive 3 meters away, right? So after 2 seconds, it's going to be positive 6. After 3 seconds, it's going to be positive 9. Okay. Now remember, this is where they're going to collide, right? So they collide here, and now ball 1 is moving at a negative 1 meter per second. So what happens to a negative on our position time graph? Okay, this direction here is positive. Negative is going to come back this way. So negative 1, so now we're at positive 9. So we're 9 meters away from our reference point. So we're going to come back negative 1. So this is going to be negative, positive 8. We're getting closer to our reference point. A second later, we're going to go another negative 1 meters, which is another meter closer to our reference point. So we're going to be at 7. And then another second later, we're going to go another negative 1. And we're going to be there. So this is our position time graph for ball 1. Now, this is where they collide, right? So this is where ball 2 is at the same time. So how fast was ball 2 going before the collision? Well, he was going negative 3 meters per second. So he was actually coming in this direction. His graph is going to look like this. It's going to have a negative slope to it because he's moving in the negative direction. So he would have been up here somewhere and is coming this way. So they're going to come and collide like this and go off in some direction. So if he was at 9 at 3 seconds, a second before, he would have been 3 meters away. So he would have been at 12 meters. A second before, he would have been 3 meters away, so he would have been at 15. At the beginning, he would have started at negative 18, which makes sense, right? So ball 1 and ball 2 are traveling with the same speed, just in different directions, right? So ball 1 is going 3 meters per second this way, ball 2 is going 3 meters per second this way.